வீடியோ ஆடும்.
A very good morning. So, I'm happy to inaugurate the department-wise conferences which is scheduled from this month onwards. And you'll be having a lot of conference happening in the month of April. And to start with, it is chemistry department. And I take this opportunity to congratulate the department HOD, Dr. Bharti, for all the initiations and the progressive growth which is to be shown in the department in the coming days. And as a first speaker, the conference is scheduled on the topic exploring local bioactive principles through bio-orthogonal tools. I think by this time everybody would have been familiar that Dr. Bharti is very known for docking analysis. So she is an expert who can deal with. So take this opportunity to learn so that it will help you in the near future wherever you're getting employed, it will be a learning platform for you to encourage your own self. So I welcome Bharti, and I also wish other departments to successfully program all the conferences which is scheduled right on time and deliver the right phase of time. And luckily, we have all experts from various fields which has been scheduled. One slot will be internal speaker and one slot will be external speaker. So the academic year plan. And every 3 months once, we'll have 1 month exclusively allocated for conferences, only 1 day. So this will give you more learning than the textbook learning, which will have really deeply practical learning from the experts. Leave around the regular textbook learning, which will be only useful for your exams. Whatever you learn conferences and seminars, guest lectures only going to help you in terms of interview or in terms of any upgrading your career goals wherever you are planning to go and join. So in the interview, you will have a courage, confidence that you know something on whatever their question being asked. So yeah, let me wish this conference proceedings a great success for all the departments. Thank you.
Good morning, everyone. Let's begin the session with Amrita.
நீராடும் கடலுடுத்த நிலமடந்தை கெடிலொழுகும் சீராடும் மரலமென திகழ்வளர கண்டறிகிறது வெட்கமும் அதிர்ச்சிறந்த திராவிடனும் திருநாடும் தக்க சிறு பிரிவுகளும் தரிதனும் இலகமுமே அத்திரக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனே உன் சீரிழமை இறப்பியத்து செய்ய மறந்து வாழ்த்துமே வாழ்த்துமே வாழ்த்துமே.
It's my great pleasure to welcome you all to this prestigious national conference on exploring herbal bioactives through bioorthogonal tools, organized by the Faculty of Pharmacy and the Department of Pharmaceutical Chemistry. Today we are honored to host eminent speakers, respected dignitaries, faculties, participants. Your presence truly adds value to this academic gathering. Now I hand over the session to Mrs. Kavya.
A very warm good morning to our respected everyone, faculties and my dear students. It is my great privilege to introduce our esteemed speaker for this section, Dr. G. Bharatiman, who is currently serving as a professor and head of the department at Faculty of Pharmacy, Sri Balaji Medical College and Hospital, Tamil Nadu. Dr. Bharati, with her over 40 years of dedicated teaching experience, during which she has demonstrated expertise in all areas of pharmaceutical chemistry, including organic chemistry, medicinal chemistry, and modern pharmaceutical and medical techniques. Inspired mentor, guiding numerous academic and research projects, a strong foundation for the future pharmaceutical professions. Her research contributions are noteworthy, with a focus on in silico studies, synthesis, and characterization of substituted heterocyclic derivatives. She has made significant scholarly contributions, including 4 patents, 3 book chapters, and more than 20 publications in reputed peer-reviewed journals. In recognition of her excellence in academia, she has been honored with Best Excellence in Teaching Award. We are truly honored to have such a distinguished academician with us. Today, I kindly invite Dr. Bharatiman to deliver the section. Thank you.
Good morning, everyone. Today we will go on to the presentation. So, the topic is taking insight cells. So, see, when you are in the younger stage, you will be using this building blocks, isn't it? For building cars and house, whatever you would use, whatever you think you will make it, isn't it? Just by clicking one building block with other building block. Just like that, reagent 1 and reagent 2 will add just by click and then you get a product. Okay, without any byproduct, only the particular product because it is putting inside the cell. If you are getting the byproduct, you will produce unnecessary side effects. So the scientists have found this deep method to design a new molecule which occurs inside the cell. That's why the name bioorthogonal chemistry. Any molecule which the reaction occurs inside the cell is said as bioorthogonal chemistry. Okay, next. So, students, you love simple answers for difficult questions, isn't it? For a difficult question, you need a simple answer. So, for providing simple answer to a difficult question, for designing a new molecule, 3 researchers received a Nobel Prize in the year 2022. Okay, they are K. Barry Sharpless at Scripps Research, USA, and Leonie R. Alfonsi, Stanford University, USA, and Northern Mental University of Copenhagen, Denmark. So, for designing a new molecule, it has to undergo subsequent reaction. Starting with its A, then you are getting B, then you are getting C, subsequent reaction has to occur, and finally you are getting a product along with byproduct. But researchers what they have done? They have designed a molecule, but it does not give any byproduct. So that's why it has been written as wrong there. No need of synthesizing the byproduct. Only the product is enough. That is the thing they have found. Researchers have found. So this is what I have explained first. Reagent 1, reagent 2. Just by it, you are getting a product. See the picture. The 3 researchers are standing there. Holding is the chemical molecule. Just by joining, they are getting a new product. Okay, that is the thing that we get here. The picture resembles the click method for designing a compound. These are all the contributions of the 3 researchers. What Barry Sharpless has done, he has coined the term click chemistry. Okay, so it is nothing but radical chemistry, where the reaction method will be, but the byproduct will be avoided. That is the contribution he has done. Next, Morton Mendel. Morton Mendel has found the copper catalyst. By using copper catalyst, they are designing compound. Is it copper is good for it? No, it's not good for it. But they have found this copper as a catalyst to design the compound. Next, Leonie Alfonsi, she is the main hero for designing the bioorthogonal reactions. She only found the bioorthogonal reaction. What are the reactions these people have found? That has been sent inside by using her research work. By using the research work, she has found the bioorthogonal reactions. So usually for doing a synthesis, what you will be using? You will be using a round bottom glass or a single glass. Okay, for synthesizing a compound. Next, after synthesizing, what you will do? You will be testing with the cells. Okay, you will separate the cells and you will be checking. For example, in case of cell culture, first you have to check whether it damages the cell or not. Then you have to check. So for that, you have to use cells or in vitro study you can do. In vitro assay method, not to check the toxicity or whether it damages the cells that you can identify. Then apart from that, you can use the animals in vivo study. Especially what sort of animals you will be using? Zebrafish and mice or mouse you can use it. Next, at last, you go for human study. Okay. Next. So, you should know what do you mean by biological reactivity space and bioorthogonal reactivity space.
Biological reactive space is nothing but our body contains numerous molecules. For example, DNA, protein, nucleic acid. Okay, so the compound which you are synthesizing in any compound that interact with the molecules and things activity, that is biological reactive space. Whereas bioorthogonal reactive space, it does not react with the DNA or protein or nucleic acid. It reacts within that cells which is inside the living system. That's why the name bioorthogonal reactive space. Okay. So Larry Sharpless, he has what he has done. Usually, the chemist or the researchers, what they will do, if they want to synthesize the molecules, especially they will aim for natural molecules. So for synthesizing the natural molecule, it is very difficult, it is tedious, and it's time consuming. So for example, neoprene is an antibiotic. Okay, so it took 6 years to synthesize the compound in industry. Okay, so what this Larry Sharpless has done? He has found he took the biomolecules as a main choice. So biomolecules contains all surrounded by carbon atom. But the lack of chemical right between one carbon and another carbon lacks reactivity. Between one carbon and another carbon lacks the reactivity. And what he has done? He has done artificial activation. Artificial activation to activate the carbon to react. But it gives unwanted byproducts, loss of compounds. So that method also it was left. Then what has happened? He has used the nitrogen oxygen as a bridge to make the reaction possible without getting any byproduct. The concept is you should not get byproduct, only the compound you should get. For that, this nitrogen oxygen is used as a bridge. Yes, this is the complete reaction they have formed. Okay, what they have added? They have added azide group, then they added alkyl by using copper and palladium as a catalyst. Okay, so by using this copper as a catalyst, what happens? It forms a ring moiety, triazole it forms. This is click chemistry, just by a click. Okay, so what is starting with the azide, treated with the alkyl in the presence of copper, it forms a ring closure, which is triazole. But it is very much tedious to synthesize as it is triazole. So this is one of the simple method. This triazole is mainly used in pharmaceuticals, dyes, and agriculture, and for making chemical bonds that have been used. So this water method has dynamic methods for finding potential pharmaceutical substances to stop the pathological process. Yes, this Bertozzi has said no, bioorthogonal. So her main aim was to focus on the glycan which is present above the cell. Okay, so this is every cell, and this one is cancer cell. Both of them contains glycan. Above the glycan you have the sialic acid. This role of glycan is to protect the cell. It protects both the cells, whether it may be healthy cell or cancer cell. That's why due to the abnormal replication, you get the cancer problem. Okay, so our idea was to introduce any group to the sialic acid. That is our idea. If you introduce sialic acid in any group, the glycan gets unmasked. If you are unmasking, you are taking the glycan out, the cells will be open. So after some immune cells will go and invade that cancer cell. That is the concept she wants to do. Okay, now we'll see one by one. So while having that idea, she attended a conference. Okay, he is a man who was present at the conference. He is Dr. Werner. What he has said, that is monosamine, which is metabolite precursor of sialic acid. Monosamine is the precursor of sialic acid. Usually in that R, NHCl or R, in that R, usually CH3 is there. But what this man has done, he has added many carbon atoms. And it undergoes biosynthesis to form. See that monosamine gets assimilated and gets introduced into the cell, glycan, and acylated monosaccharide. So based upon this, she has an idea. Why we can also do the same thing? She has an idea. So based upon this, she has given a cartoon picture. This is a cartoon picture. So this is the cell membrane about which glycan is there. Okay. So the glycan, that unnatural sugar is attaching. So at present she don't know what is X and what is Y. That is what she wants to. She is going to research now. She wants to add one group there. Then Y group here. Why the green color is represented? It is a fluorescent probe. Why you are attaching probe? Not to identify. You can't ask this. You can say probe is there. Not identify. Only by observing through microscope or anything you can identify the cells. That's why probe they are using. That is attached. And they have a person. Next. So this is famous reaction. Schrodinger reduction. We also see neutralizing. Schrodinger reaction. His name is Dr. Hermann Schrodinger. Phosphine treated with azide. It forms an adduct. Phosphine treated with azide forms an adduct. And finally, upon adding water, it undergoes hydrolysis. But if you are giving this inside, what happens? It undergoes hydrolysis and removes RNH2. But we need that end inside. But RNH2 is removing, it is getting removed. So we need that end to be attached to phosphine. Okay, understood? That end should be attached to phosphine, but it undergoes hydrolysis. When you are giving inside the body, what happens? The RNH2 gets removed and this phosphine also will be inside our body. So this also she dropped. Based upon this, one of our student, okay, Dr. C, research student, what he has done, she has substituted ester group there. See there, ester, see the one of those is there. So when you substitute ester, she has added azide, same, it forms an adduct, and then it does not undergo hydrolysis. What happens? The NH is there, isn't it? So the name deviation, based upon Schrodinger, she has designed the compound. That's why the name Schrodinger deviation. So designed a new compound. Her student, what she has done? She has used the cell culture. She poured this deviation product into cell culture. That cell doesn't get damaged. So what she has an idea. Why can't we use this phosphine into the cells? So she has an idea. Okay. Now related sialic acid N3. So here, based upon this, she is going to add. Just she got the way where you can add, what are the compounds you can add, how to add, like this she has got this. Next. So see, the sialic acid, monosamine is associated. Then it binds with sialic acid. Along with that, it needs fumose, galactosamine, likewise it is getting associated. These three compounds get associated and it moves to glycan. The activity is glycan. So the cells get open, cancer cells get open, so it gets invaded. Next. Yes, she has done. See, we have seen by using cell culture. She used in vivo study also. Her student then her student Danny Dubé, what she has done, she used that associated monosamine. She injected into the mice. Okay. See that it gets bind to a associated monosamine binds to sialic acid. About the glycan, cell membrane is there, glycan is there, then associated group is there, CN3. Now what is the next step? You have to add phosphine. Phosphine is added along with fluorescent drag. Next is the phosphine along with the fluorescent drag. Identify where it is present. Okay, so the phosphine is going to the sialic acid. Okay, this is given by flow cytometry. It is a technique where you can identify the cells, both physical and chemical characteristics of the cell by laser beam. That is flow cytometry. Okay, next. So these are the reaction. That is for organic chemistry. First, what what is in 1963, azido treated with an alkyne, it forms a ring closure, but it's very slow, found by Rolf Christian. And it is very slow. Then what they are copper. They are 2002. It is fast, but it produces toxicity to the cells. So it is also like a copper catalyst. Next. In 1961, she underwent many research papers to identify without copper we need a compound. So, see that is cyclooctane treated with phenyl azide. So it produces it's very closer to you are getting product, but without the catalyst. So this is the idea. So based on this one, this is the basic what the purpose here want to do. Okay, next. So she wants to look at the experiment wise. So she has selected zebrafish. Okay, zebrafish which is translucent. So by using microscope you can see that you can see the color of the road. Okay, so first then acid galactosamine. Then it is inserted in the zebrafish. Entry is even attached there. Then you are using the cyclooctane it along with the closure group. So it getting attached there. Then tricarboxyl ethyl phosphine. TCEP is tricarboxyl ethyl phosphine you are adding. So phosphine again attached to the probe. Okay, next you are selecting remaining unreacted M3 again you are join again to have different probe. In order to identify how many unreacted azide has been set there, you are using different colored probe. Here is red, green, like this you can use so next. So this is it's a dynamic representation. She is Karen person. She mainly studies mapping of genes and proteins to understand how cells work. And also she develops interesting glycans. Glycans are complex carbohydrates often sit on the surface of the proteins and cells. See the cell nucleus. She is adding the sugar attached to the azide. Azide one she is attaching. Next, it is attaching to the glycan. See that glycan is there. Glycan above the azide is there. Then she is adding that frozen probe. Then it is getting attached. Then it marks the glycan. Next. See the picture there. That the blue color represents the nucleus, the green color represents the frozen probe. So it is masking, it is taking out the glycan and removing. So it unmasks the cancer cell. See there, two reaction goes on bind to the cell. Then what happens? The antibody goes and binds to the cancer cell and unmasks it. You can use it to treat cancer cells, but still it is under process. Next conclusion. So it provides high selective and non-invasive toolkit for labeling, imaging and modifying biomolecules in real time. The field has been driven by pioneering works such as the of Karen Bertozzi, whose contributions can establish bacterial reaction, function leading cells, and biochemical reaction like azide and alkyne cyclosion are fast, specific, and compatible with the physiological condition, making them ideal for biological application. Next, in conclusion, bioorthogonal chemistry bridges the gap between chemistry and biology by allowing precise molecular control in complex living system. It is expected to play a crucial role in the future of personalized and targeted treatments. If you have any doubts, you can ask. You can also do research works by using different substituted alkyne product. Alkyne with started with azides. Okay.
Participants, you have any doubts, you can ask. Do I have any doubts? Nobody? Thank you. Do you have any questions, you can ask.
Thank you, Karina, for this wonderful session. I hope students understood the concept of this biological chemistry. So, you go for the lunch break and please resume by 1:20. Class, go back to your classes. Thank you.